Okay, well, let's get started. And hello, everybody, and welcome to this is the second of the Kickstarter Colloquiums. These are intended to be a platform to feature work that's been done by many teams, particularly from the Rubin Science Collaboration's TVS, Stars and Milky Way, and the Solar System collaboration. And their goal is overall to prepare for a wide range of science with the Rubin Observatory. The colloquia will be taking the form of several short talks by representatives of each of the projects, after which we'll have time for questions. And as you've just heard, the colloquia will be recorded, and the recordings will be posted on our YouTube channel for the benefit of those members who can't join us in person. So if you don't wish to be recorded, please keep your camera off. And one last thing is, in the interest of hearing the speaker during the talk, please mute your microphone if you're not actually speaking. So we'll kick off today with a talk from the Solar System Science Collaboration by Gustavo Benedetti-Rossi, who is going to tell us about the new software program he's developed called Occultin. So take it away, Gustavo.
Thank you very much. Okay, you can see my screen.
Yes, we see your screen.
Okay, it's perfect. Okay, so first, thank you very much, Rachel, for inviting us to this presentation. This was a very pleasant experience to lead this to the development of this interface. So we call it Occultin, which is the short for Occultation Interface. And it's an interface developed for stellar occultation date reduction, and it's based on SORA. And we had a huge help from people from Linea, which supported us a lot during the development of this project. I have also to say that Rodrigo, I think he's here with us. He also helped me a lot. He was the co-I of this project. And our two students, João Vitor and Maísa, and the IT team led by Mozart Silva, and which we also had huge importance on this development. So basically, I'll talk about very shortly about the stellar occultations. We make a connection with citizen science because stellar occultation needs the citizen science to be well performed. Also, a quick words on SORA, a Python library we developed to work on stellar occultation data. And finally, the interface we developed here with this Kickstarter project. And some final words. So basically, stellar occultation is the variation of the star flux along a short period of time due to the passage of a solar system object in front of it, causing an occultation. So basically, it's an eclipse or a transit. So you have here a star, and the body in the solar system passes in front of it. And during the time, so here I have like 5 frames with the body moving along, and the star is fixed. So in fact, we measure the brightness of the star, and when the body passes in front of it, the star flux here drops, and then we have here the star flux again. So if I have, it's a very powerful technique because besides the main body, we can also see some evidence of nearby stuff around the body, for example, rings, jets, or atmosphere. So we can also detect this. So the rings of the Uranus and Neptune was discovered by stellar occultations, and more recently we participate on the discovery of the rings on the small bodies like Cherry Claw and the dwarf planets Haumea. And we have some more other suspicions on Chiron, for example. So about the citizen science, so all these occultations we have a huge team of cooperation led by 3 main groups. We from Brazil, we call the Rio group. we also have two other teams led by Bruno Sicardi in Paris, the Observatory, and led by José Luis Ortiz in Granada in Spain. So all these red dots here in the map are both professional and amateur astronomers that participated at least once in our observation. So it's a very collaborative work we perform all around the world. And so if you want to know more about what we do and everything, we have this the predictions for stellar occultation here on the site. And here we have a kind of a portal that we start to organize all the data that comes from those observations. And SORA is a library that we developed. So it's led by Altair. It's a co-worker of mine. We have this paper published recently. And it's basically a Python library that compile lots of programs and routines that we use it to use for stellar occultation data. So it's divided in a few blocks. So you have the ability to work between them, and the user can create its own pipeline. So we have the ephemerides, the body, we have the prediction, and then we have lots of stars that are candidates. We can use other bodies and make the same stuff. And then we have the occultation. Then the observer gets in more than one and can observe and get the light curve and make observe the occultation. And then we have some extra stuff here to analyze the light curve using the physical models and everything, and project the chords and the sky plane so we can derive physical parameters of the object. So thinking about that, we have the SORA is a Python library based. So you need to more than know what to do in reducing data, stellar occultation data. You have to know how to reduce the data. So it's a very kind of complicated process. And the idea of this interface is because we're expecting that with the LSST it will increase the solar system inventory, and we need an easy access and easy processing stuff to do with the data in order for the people that are not too involved in science to be able to develop and can also help us reducing the data. So it needs to be accessible and adaptable. So the interface is based on SORA. It's not an interface for SORA, so it's based on SORA because SORA is it's shown that's a powerful library. And now we have the idea to build a graphical user interface so we can make it very quick, very practical. And the idea is that we can also integrate this interface with the portals that we already use for stellar occultation, such as those that I showed before, like from Paris Observatory and the other one that we used to organize the data. So the timeline that we had was like something like this. So we had we lost a few months, few days planning, studying how everything was going to be, how the windows were to be showed, the backend, the minimum value product. Then we had to make a follow-up to this was one of the main parts that we need to translate the scientific process to the IT team, because they had to understand what we needed to do and what the interface needed to do. So we hired an IT team so they can help us developing the process. For then, after a few time, we had the first version for Windows and Linux, with provisory version with only on predictions. Then we made a very interactive loop with every week we had weekly meetings and to discuss corrections, search for bugs and errors, and they developed new versions, and so it was an infinite loop. And this was also very important because the students could also help us finding those bugs, and so they had to learn how was the process for the reducing the data, and also interacting with the IT team to understand what was their need. So finally, we had this 0.97 version. It was the latest stable version, but it's not the last one. So we still are doing. So just to be quick, I'm also almost finishing. I wanted to show you some of the windows. So here is the loading, the presentation, and then we have an interface for logging. So we have a user, and the user selected the project, and so this is the idea is that this could be integrated in Linea portal. So this more than one user can work on a project to follow up and help the development of this project. So for now, it's it was made to work locally, so you have only on your computer. So then you have a very step-by-step process. You choose the project name, you put a description, then you select all the objects that you want to make predictions, and it makes online queries on horizons, JPL, and after that, you select the time that you want to make those predictions, the star magnitude that you want to look for it, the star catalog you want to use to make the predictions. Usually we use Gaia, and it's here it's DR3, but we're now improving it to DR3. And then you have some other few parameters that are important for occultations. And then you have a last one, a summary of everything that the user chose. And then you have the jobs. You have a line that will show at some tables with some important information. And here you have this tree that will present all the predictions. So after the process are done, you for every object, you have a list of predictions. And if you click on one of them, you have the occultation prediction maps with all the important information the user needs to have. And then we have the light curve. So after the occultations, we don't have tools yet to work on how to obtain the light curve. So the observer has to do it on its own. But for the amateur community, there are a few softwares already done, so we do not need to worry about that. So we have the user can put some stuff, some information here about the light curve. So the name, the data file with the time and flux. That's the two main column that is important. The reference instance that you want to put from this file, and if you want to put an error and everything. So after you load the file, it will make some plots, and then you can use all these functions that you need to work and analyze this light curve. So when you edit the light curve, you can change the distance, the velocity. The user has total freedom to work It's not, so it's note that it loads automatically for a standard project, but if you are more experienced, you can change some of these parameters to obtain better results. So you can normalize some. This is already normalized, but some light curves are not. That's beautiful. And then the user will obtain the instance that this flux that drops and the flux of the star returns to near 1, which are the most important values for to obtain from these light curves. So we call the immersion and immersion times. And then with those two instances, we use to make the light curve fit. And then the light curve here, the user has lots of freedom to lots of parameters to work on that. And after everything, we show all the plots that we need and a summary with all the information that was obtained. That's if one can quickly analyze and verify everything. So after you have the chords, you can first we can change the colors and edit everything and plot in the plane of the sky, and finally we obtain an ellipse. That's the main goal of that's to obtain physical parameters of the object. Also we have a very long summary here with all the parameters and everything, all the information if one needs to check. And everything here was documented. So the full documentation on the interface and use and operation was done by the two students, João Victor and Maísa, with also the practical user guide it was everything developed under our supervision, but they developed most of it. And we are preparing the Git repository to be available. So for now, we are only available on demand, but it's available if you want to test. And that's it. Thank you very much. I would like to thank you, especially the Linea, and that will be an IDEC for LSST. So they are also preparing lots of stuff. Thank you very much.
Excellent work, Gustavo. Congratulations. That looks like a fantastic interface for many of your observers around the world. Do we have any quick questions? I'm a little bit mindful of time, but are there any questions for Gustavo? I will take the opportunity to ask, have you had any of the many observers you have around the world? Have they acted as beta testers for you?
Not yet. We are finishing some corrections that we found some errors in SORA, in the last version of SORA. Oh. So we are correcting SORA before making it official and send to first to our group and our international collaboration, and so everything. So as I told you, it's on demand, so it's not officially to be distributed, but I hope soon we will have this.
Very good. I look forward to the package being formally released. And thank you again for your talk.
Thank you.
In the interest of time, we will move on to our second speaker. We'll have Tomas Ahumada, who will talk to us about Kilonovae with Rubin, turning alerts into science. So take it away, Tomas.
Great. Can you see my screen? I think
yes,
it's loading.
It's just coming up now. There you go.
Okay, I do have a crappy internet connection, so I hope it doesn't, collapse. So thank you for the invitation, Rachel. I'm Tomas Ahumada. Formerly a grad student at the University of Maryland. I was working also at NASA Goddard with Leo Singer and Brad Senko on gravitational waves and optical follow-up of short gamma reverse. But this effort was performed at the Observatory here or the Astronomical Observatory in Rome, OR. And now I am a postdoc at the Caltech at Caltech. So where do I start? I just wanted to mention first that this is an ongoing effort. There are two papers that are in the draft stage, one led by me and the other one led by Fabio. Fabio did his talk last week, I believe, or maybe 10 days ago. So the idea was to sort of like merge these two topics. The idea was to analyze how to get Kilonovae from the alerts and that Rubin will eventually provide, and what to do with those alerts, and how can we estimate different parameters and energies. That was Fabio's work that was presented last week, and now I'm going to dive into my part of the science. So this is a little bit of the background. If it loads effectively, the idea was to show a little video to motivate. Perfect, it's coming now. Here you have two neutron stars that are orbiting each other, and you see on blue sort of like the representation for gravitational waves. These two neutron stars will eventually merge, and then light. So we have light in different wavelengths, different energies, and power in different transients. So the idea was now to use Rubin and see how are we able to detect this. So there are different ways to detect gravitational binary neutron star mergers. This is the first example we had in 2017. This on the left, you have the probability map derived by LIGO Virgo, Fermi, and Fermi integral, because this was a joint detection in gravitational waves and in gamma rays. So you have here the gravitational wave time frequency map on the lower right. You see how as it goes in time, it increases the frequency until eventually it merges. And then 2 seconds after, there's a GRV coming from this object, and it was detected by both Fermi GVM and integral. I also plot here the light curve of the transient in the optical. In green, you have the G band, and in red, you have the R band. This is just to show how fast this is fading. So you have sort of like it decays a magnitude and a half in almost 2 days. So what is happening? What are we seeing? So you have a binary neutron star merger in which the central engine, it's either a hypermassive neutron star or a black hole. It's powering then a jet here in purple. That jet will collide with the interstellar medium and generate an afterglow. The material that's around and that it's part of this merger will undergo the R process nucleosynthesis. This is basically a lot of neutrons rapidly captured that will eventually decay. This decay will power what we call a kilonova. So this kilonova is a very fast fading transient. It's sort of red. And the idea was to use this to measure different physical phenomena. And one of the properties of this kilonova is that different models will predict different sort of decays, and different configurations would have different effects. But normally you would have a transient that is decaying faster than 0.3 magnitudes in the R band. So you have here a plot from Andreoni et al. 2020 showing that most of the models will do show that fast decay. And the empirical likelihood that we have from 17/17, that's the day that these two these two neutron stars merge. And that also shows a very similar behavior. So why is this important? Because we can learn a lot of stuff from this merger. Primarily, we think that this is one of the origins of heavy nuclei, but also we can touch upon physics on regarding to the remnant merger, the jet physics, the high energy particle acceleration. You can see how it will light up the entire electromagnetic spectrum, and it's more interesting because it's also a multi-messenger source. So we can analyze it through gravitational waves, but also in the electromagnetic spectrum. The question is, how do we find it? So as I mentioned, you have a gravitational wave source, you have a very bright electromagnetic source as well. And different people and different teams have tried different ways to find this object. So this is sort of like a review in the past 2 years, I guess. The third observing run, there were a bunch of teams trying to observe and try to catch this object. We couldn't really find anything as a community, but we did do a very good job at observing most of the alerts, the gravitational waves alerts. There are relevant articles over here, and this is just an example of a gravitational wave map. So what usually happens is that a telescope will tile the region, as you see here, and then would observe, and then candidates will come from that that search. The idea is we are trying to find something that fades very fast and that shows signatures of either gamma ray burst or kilonova. So we didn't really find anything, but we've been able to constrain kilonova models and stuff like that. Other people have tried to find short GRBs, the optical counterpart to short GRBs, because when you have two neutron stars merging, or a neutron star and a black hole merging, you expect a accreting black hole or a rapidly rotating neutron star that will produce these very, very fast jets, and that would produce this gamma ray emission. So when you see a short GRB, you would it's likely that this is linked to one of these objects. So people have tried to look for these objects. What are the optical signatures of this? When the jet interacts with the circumburst matter, it will produce this afterglow that is visible from the X-rays to the radio. So similarly, we have people have used Swift or different satellites, gamma ray satellites like Swift or Fermi to look for these objects. This particular image, it's from my late paper. We tried to look for these objects, but we really couldn't find anything. The main issue is that we're finding a lot of contaminants. So what kind of contaminants are we talking about? So mainly long GRBs. So these come from collapsing massive stars that will produce, in the center, it will collapse, and then it will eventually produce a supernova. We also have supernovae that are contaminating our sources. So as you may have heard before, there's a bunch of different types of supernovae, from thermonuclear supernovae to core collapse supernovae, and they all have different signatures. You have here sort of like a schematics of how are they different, how their lighters are different, and some of them are even linked, as I mentioned before, to long GRB. So there's like an afterglow perspective to that as well. We have found tidal disruptions events on these endeavors. Here you have a set of light curves from Hammerstein et al. 2020, just to show you how diverse the light curve space for tidal disruption event is. Tidal disruption events are basically a star that's eaten by a black hole when it's tidal disrupted. You have also active galactic nuclei that are contaminating our sample, because it's a very stochastic behavior. You don't really know, it's really hard to predict. And here again, a bunch of light curves that show these objects are very, they have different behaviors. So particularly here in our example, it's our investigation. We're trying to find the optical counterpart using either afterglows or kilonovae. So how did we do that? Usually, when you think about synoptic surveys, you can think of they are looking into a volume, a sphere around Earth, basically. CTF, for example, it's mounted in a 48-inch telescope. It looks up to a magnitude of 21 in the R band. So it has a certain volume that it's actively looking at. Within this volume, it generates around 10 to the 5th alerts per night. But with Rubin, the universe will be, the observable universe, it will be much larger because it's a larger telescope, but also it's much better overall. This survey will generate 10 to the 6 alerts per night because, again, it's looking to farther into the distance. So what did we do? We simulated our own Rubin universe. We created light curves of all these transients over here. So supernovae, tidal disruption events, gamma ray burst, kilonovae, and active galactic nuclei. We simulated how these light curves would be observed by the Vera Rubin Observatory. And then we feed them to different filters to try to catch and quantify how well are we doing catching this kilonovae. So going back to the method, we generate a light curve from either a model or a real source. So this is just an example. So you have an afterglow here. And in this case, I'm using CTF as part of the example. So what if CTF observes this transient 0.4 days after it happened, and then another observation happens 1.4 days and then 2.4 days? What would the light curve look like? So if you have that the CTF limit, it's around the 21st magnitude, whatever observation that happens after a day and a half would be lost because it's not visible for CTF. So we take that into consideration as well by randomizing magnitude limit distribution, because we don't really know how well Rubin will perform, but we do have estimates on how deep are we going. So we just generated a distribution and we randomly picked around the magnitude limit that it's available for everyone. And that plus a schedule generates a light curve. So to generate each of the transients, we were careful into taking into consideration the number of events for each of the transient type. We estimated the number based on the event rates and the Rubin limits, scaling by the magnitude, absolute magnitude that is relevant to each transient. So, for example, transients that are more energetic, you would have a larger volume visible to LSST, and that will generate a larger number of events. We try to use realistic light curves based on both models and empirical results and empirical objects, basically. After we generate a light curve, we randomize a coordinate to both look for things that are around, saying stars or galaxies, and to apply extinction. We also randomize the time that it's observed so that we can cross-match with the minor planet center to get the distance to close by minor planets, either asteroids or meteorites. This will generate the entire light curve with different metadata that it's available usually on for scientists to use as filters, and that is packed as an Avro alert. So we generate basically alerts for each of the transients. These alerts we then feed to the MongoDB Compass. The MongoDB Compass is a software that allows to use and filter clusters of information. So we upload all the documents, all the Avro alert packages. So then we can use a filtering scheme, and then we can play with this filter to check what are the most prominent sources and what are the features that we can use to try to get the most Kilonovae in this case. So the filtering criteria that we had developed takes into consideration that the object is real, because we generated obviously the object, but more importantly is that the alert has more than one detection. As I mentioned before, there are situations in which because of how fast this is fading, it could go from one night being detected to the second night, or the second observation or third observation to be non-detected. Then we check for stars that are close by and try to avoid things that are moving. And since this is random, the idea was to get a sense of how much these features would affect the filtering criteria. And more importantly, part of the filter is to only look into the things that are fading faster than 0.4 magnitudes a day. With that, for each of the transients that we simulated, for each of the class that we simulated, there's a table in the draft that tells you what's the rate that we use, the number of sources that we generated, but also the number of sources that have more than one detections. And basically that allows you to see what are the sources that are not being detected and why are not being detected. So we have, in order to be part of our filter, you need to have more than one detection. Then you have the number of the ones that passed the filter, and then the ones that were detected as fast fading. And before wrapping up, this is just the part of the results. So on the left, you have a pie chart of all the kilonova that were generated. So out of the 100% that were generated, only sort of a quarter of them had more than one detection, and only 2.6% of them were fast fading. That doesn't mean that the rest were not fast fading, but that only means that we didn't have enough data points to measure the fading of the sources. So there's a bunch of sources that are detected more than once, probably in two different filters, but we are not able to measure the fading of those sources. So then these sources are not considered in the final cut. They do not make the final cut. And there's a large portion of those kilonova sources that were not considered because they did not have more than one detection. That might be linked, that's part of the future work, to see if it's linked to the cadence of that we chose, or how can this could improve. The pie chart on the right shows the final set of sources. So that pass our filters. We have sort of close to 4,000 sources, and only 5% of them are kilonova. The rest are either GRB afterglows, supernova type 2, or TDEs. Particularly, if we go to the numbers, if we are trying to be as realistic as possible, out of those 4,000 sources per year, we can reduce that to 11 per night. So 11 sources would pass our filters per night. And we can now see what are the main contaminants, so we can adjust our follow-up resources to try to rule out whether they are GRBs or TDEs and stuff like that. In the future, we would like to add more contaminants, cataclysmic variables, and on other sources that are very fast fading. But the idea is, how can we change our filtering strategy, but also the cadence of Rubin to tackle more and try to get more of this Kilonovae that it's only basically 5% with the numbers we have now. Out of the sources that are detected, this is the distribution of the sources that pass our filter. And I guess good news and bad news. Kilonovae are usually red, and most of the signatures that could allow us to separate them would be visible on the near infrared. But with an 8-meter infrared spectrometer, not many of the transients will be bright enough for these capabilities. But we would have a good number of them available for optical spectroscopy, sorry. And the idea was just to get an idea of how many sources we would be able to observe and follow up with other facilities. So what's in the future, I guess, it's important to measure also the impact of near-infrared facilities. There are a bunch of small surveys that are going to be in the north and south hemisphere, and how can we use more photometric data points to vet these different transients. It would be interesting to check what are the impact of different cadences, and what if we apply a target of opportunity, for example. And it's an ongoing process. It's hoped that Rubin will be on and working for the 5th run of LIGO and Virgo, but there are other target of opportunities that could be interesting, such as the following up short GRVs or even long GRVs, as now the literature is changing quite fast. So with that, I think I'll just stop and thank you for your attention.
Thank you very much for that excellent talk, Tomas. That was fascinating. And I'm sure there are a number of questions that are pressing from the audience, but in the interest of time, I'm going to suggest we move on to Christina's talk and then come back if we have time at the end to further questions. So thank you again, Tomas.
Sounds good.
So Christina, feel free to share your screen. So our last talk of this colloquium will be Cristina Andrade, who is staying on the subject of Kilonovae and the influence of the selection of Rubin's filters and the time selections. So please carry on, Cristina.
Okay, so can everybody hear me?
Yes, we hear you.
Perfect. To begin, I will introduce myself. I'm Cristina Andrade. I'll be presenting the effect of the Vera Rubin Observatory filters and return time selections on Kilonovae detectability. This is an international collaboration between the American University of Sharjah, the University of Minnesota, the University of Texas Rio Grande Valley, and the Joint Space Science Institute. There we go. In this work, we explore the possibility of optimizing Rubin Observatory's ability to detect Kilonovae by studying both existing LSST cadences and ones provided by the project. Subsequently, by studying how detection rates are affected by filter selections, especially red and infrared filters, IZY, compared to the more blue filters, the return timescales for visits of the same area in the sky, and other relevant factors. We assess the benefit of our findings to related scientific interests, including maximizing a range of fast transient discoveries. This is a brief overview of the aspects of the VRO that inspire our research. We will be relying on the most significant part of the Vera Rubin Observatory's capabilities, which is to scan the available sky every 3 days. It makes it a primary candidate for detecting fast transients. As well, to restate what was said in our abstract, the LSST survey will be done in 6 photometric filters, and this is significant as Kilonovae have a higher rate of detection in red to infrared band filters compared to the bluer ones. So methods of experimentation. The efficacy of detection is dependent on the field view, the depth of the observation, and the optical bands, and the frequency with which a site is observed. Return times are an imperative piece of data to collect, as kilonovae are often a fast fading and fast evolving phenomenon, dimming over a span of a few days. This is compared to longer existing occurrences like supernovae. In order to test kilonova detectability, we were given access to the LSST Jupyter Lab. This environment granted us access to the LSST matrix and simulation strategies. We used a unique code designed by Igor Andrioni. We injected numerous merger events, upwards of 500,000, with a variety of characteristics, different light curves, brightness, and used that to explore the extent to which filters and cadence families will allow the Vera Rubin Observatory with various LSST cadence simulations to better detect the associated kilonovae. Cadence families being the sequence of individualized requests. The goal here is to place specific filter configurations and exposure times, among other factors, to be executed on a telescope survey. And then behind all this is the metric analysis framework. It's a software package used to process LSST surveys. The Occultin, as we call it, creates the 10-year survey. And in our analysis, we used, we injected light curves into the simulated Occultin cadences that we can see in this table. And we evaluated these surveys and studied the efficiency of Rubin Observatory for kilonova detection. The theoretical light curve model that reconstructs the kilonovae was taken from Dietrich et al. 2020, which uses the POSSIS Monte Carlo radiative transfer code, which is a numerically simulated propagation of electromagnetic radiation, in this case, a kilonovae. The survey strategies studied in this paper are from the version 2.0 and 2.1 survey simulations that were provided by the LSST GitHub, or that's where we got them from. They consist of a set of strategy variations, all of which evolved from the previous releases, so 1.5, 1.7.1. We study all the available families in the V2.0 survey strategy with special focus on the families designed for transient science, which is the baseline, the rolling, triplets, and the long gaps, no pair families. Versions 2.0 and 2.1 feature a survey footprint with expanded dust-free area, the wide, fast, deep area level visits in the galactic bulge and Magellanic clouds, coverage of the northern ecliptic spur, south celestial pole, and remainder of the galactic plane is maintained, but at lower levels. Filter balance is modified in different areas of the sky. We have baseline, which features that survey footprint with expanded dust-free area and the wide field deep level visits that I mentioned. The Presto cadences fall under the triplets family. They add a third visit within each night, repeating one of the filters using the initial pair. The idea behind the rolling cadences is to divide the footprint area into regions, and this enhances the sampling rate a region at a time, at the expense of decreasing the sampling rate in other regions. And then we have the long gap no pairs family, which extends the revisit time, originally separated from 33 minutes from 2 to 7 hours. In some cadences, the long 6 gaps are applied in all the surveys, while in other cadences, they start on year 5. So our filters. So the multi-detect and related metrics follow standard transient detection criteria. This is with greater than 2 detections, which provides information on the celestial importance of source, whereas the ZTF-REST simple and related metrics detection criteria allow for proper source characterization, i.e. kilonova discovery. ZTF-REST metrics are taken from studies made by the ZTF real-time search and triggering project, which is dedicated to optimizing fast fading transient discovery. Andrioni et al. 2021b, that was from his paper. Simple detection is vital for gravitational wave follow-ups, but is not similarly effective in regular fast transient surveys. Thus, we need additional photometric criteria to separate kilonovae from other transients. Next one. Yes, that is the next one. So then we have the time gap. We employed the TGAP metric from the source file, lsst.sims.math.metrics.tgap metrics. So we employ this to understand how kilonovae detections are affected by return times between observations in that same area of the sky. Most Rubin Observatory cadences consist of pairs of visits that occur in the same night and are separated by approximately 30 minutes, with a return visit after a few days. Current visit separations provide little constraint on temporal evolution within a night, and ideal cadences for transient discovery and similar variability characterization would be uniform in log T and sensitive to variations on all timescales. That's from Bellum 2022. And then finally, our results. So after injecting a series of cadence families into our simulation, we are able to compare them. This here is the 2.0 recovery. This plot demonstrates the Kilonovae recovery efficiencies versus each of the K&E metrics for every simulation. The cadence names can be seen in the upper right. And then for the purposes of this study, we used simulations of the baseline cadences where the filters were set to specific choices in order to put a bound on how much filter selections affected our results, as well as to quantitatively estimate what the best Kilonovae, one second, something popped up on my screen. As well as to quantitatively estimate what the best Kilonovae filter is. To abridge our results in this figure, we use the GW17081 7 Kilonovae model with a luminosity distance range of 10 to 600 megaparsecs. You can find that in the first row of table 1. If anybody wants to go back and look at that, we find that with the ZTF-RES simple metric, the baseline V2.1 cadence has an 6.6% increase in number detections from the V2.0 release. The baseline retrofit and retro baseline cadences, on the other hand, will decrease in detections by 1.4 to 5%, about approximately 5%. However, we see that the retro baseline improves over no roll by approximately 8.1%. This is speculative due to the fact that the old footprint places more visits per pointing into the low dust wide field deep range. If we look at the rolling cadence results, we see that the rolling RW 0.9 performs the best with the ZTF simple metric, but it outperforms the baseline V2.0, again, by about 5%, indicating that high rolling strength would be favorable for Kilonovae detection. Detection rates show that the I band and R band dominated survey dictate most Kilonovae detections. The I band dominated cadence received the largest number of ZTF-RES simple detections and consequently the high recovery efficiency with approximately 6% increase from the original baseline cadence. And its multi-detect metric results have a 7% increase in detection rates from the baseline cadence. The R band dominated cadences got a slightly lower rate than the I band and the ZTF-RES simple results, but had a similar 5 to 6% increase from the baseline cadence. The two filters also outperformed the rest of the filters, as well as the baseline cadence, when both multi-detect and ZTF-RES simple metrics prefixed and the ones prefixed and suffixed with blue for R band observations and for I band, and red for I band observations were considered. This overall indicates that they are prime for transient and Kilonovae discovery. All in all, we hope that these simulation runs will continue to develop a once barren framework into a robust potential for detecting Kilonovae and further our study of multi-messenger astronomy and gravitational waves. Thank you.
Thank you very much, Christina. Excellent talk. And that's interesting illustration of the tensions between some of the proposed strategies. So looking at that last plot that you had, excuse me, taking the chair's privilege of getting my question in first. If I go back to that, it seems to imply that the strong rolling cadence was the most beneficial for your science. Can you remind me exactly what you mean by strong rolling cadence?
Strong rolling cadence means that, I phrase this. Could you ask your question again?
Sure. I know they experimented with a number of different implementations of the rolling cadence. Some of them used different bands, some of them placed a greater weight factor towards the observations within that band versus at the rest of the sky. So what is it you mean by the strong cadence, the one that is preferred for your science?
So these cadence families and the individual simulations run from the cadences will have a larger variables or prominent variables. And when you have the prominent variables taking the lead compared to another array of variables, those are considered stronger. So it's like the focus of an individual cadence family. Does that make sense?
I think so, yes. If I'm reading your plot correctly, you prefer the 2-band cadence with the parameter being RW 0.9 over any of the other scenarios.
Yes.
Excellent. Okay, thank you. So are there any other questions for either of our Kilonova speakers this afternoon? I do see that there is a lively discussion going on in the chat screen regarding the first talk of this afternoon. Tim and Gustavo, have you come to an answer about your question?
I hope I was clear enough.
Yes. So,
okay, great.
A question for the last speaker, though, if I can.
Please go ahead.
One of the things that we've looked at in the solar system, and there's an issue with the rolling cadence, is if you've got very rare objects like interstellar objects, so like Oumuamua, rolling cadence is bad for those things that are very rare but very high productivity, high scientific return. What's the sort of expected on-sky rate for Kilonovae in terms of numbers per year per footprint?
That is a great question. I have that table of efficacy in front of me. Just give me a moment. I do not know that number off the side of my head. Which rolling were you looking at? 0.9.
I guess any of them at this stage.
So restate your question.
I'm just wondering about your whether the heavy rolling cadences, what your expected occurrence rate on the sky is of the objects that you're interested in, and whether a heavy rolling cadence affects that on badly or not.
So the rolling cadences were in the heavy rolling cadence range were 0.08 for the TFRS simple, but I'm not sure how to answer your question. I would love to get back to you on that. Louis might be able to help you. Louis Salazar, who's also another member of this team who's helping us write this paper. He would also be somebody who could answer that question. But I'm actually not sure.
Okay, no worries.
Sounds like a discussion we can follow up offline if you prefer.
Yeah, because the appendices is just, for my paper, is just a table of the efficiencies for each filter. We don't know the averages, and we don't know how, we haven't fully evaluated the sky maps. We've only taken the light curves off of them. So our
Okay.
Well, thank you very much, Christina. It sounds like there's a lot of excellent work has been done already and more to do.
Much more to do.
Very good, very good. Well, thank you once again to all of our speakers this afternoon. Those were 3 excellent talks. And I will be posting the recording of this video online as soon as it processes. So let's wrap up once again by thanking all our speakers. And I hope to see you all at the next Kickstarter Colloquium.